Hi, Marcus. Hi, everybody.
Hola, buenos días, buenas tardes. Hola a todos, bienvenidos a la sesión 4, Modeling in Earth Sciences. Es un gusto tenerles aquí y para empezar la sesión 4 con algunas pláticas bastante interesantes. Vamos a cambiar al inglés por ser una reunión internacional y tenemos algunos participantes que no hablan español. Hello, good morning, good afternoon, everybody. Welcome to session 4 in Modeling in Earth Sciences. It's a pleasure to introduce the first speaker. It's Jonas de Basabe, a professor here at the Sesión, and he's going to speak about an analysis of the high order and enriched Galerkin method for wave propagation. Jonas.
Thank you, Marcus. Hi, everybody. So, as Dr. Grosskar already mentioned the title of my talk, let me summarize the objective. We would like to formulate the high-order enriched Galerkin method for wave propagation. We would like to implement it for acoustic, elastic, fracture, and or anisotropic media, which covers a wide spectrum of wave propagation problems that we're interested in. And we want to compare the enriched Galerkin method with the discontinuous Galerkin and the continuous Galerkin, or basically the spectral element method. And we would like to, I will show you some examples of wave propagation in fracture and anisotropic media towards the end. So what's the motivation of this? Why do we want to propose a new method for wave propagation? Well, first of all, let me mention about fractures. Fractures are a very common feature in the subsurface. For example, when you're driving on the highway, maybe you see landscapes like this one on the picture on the right. You can see the rock formations, and you basically always see that the rocks are fractured. And in the subsurface is not very different. Fractures are a very common feature, and they are not only common, but they are interesting because they are important for the oil industry, for geothermal industry, and nowadays they are interested in the CO2 sequestration, and fractures may form escape paths for the CO2. So we also need to have a good understanding of the presence of fractures. And similarly for the nuclear waste, whenever they store nuclear waste, they want to make sure it's not going to escape. And beyond the earth sciences, fractures are also interesting in several branches of engineering. For example, in civil engineering, you may want to know the presence of fractures before things like this happen, from the picture on the right below. Or what happened, for example, in Mexico City recently, that the subway collapsed. So there's something called in engineering the non-destructive evaluation, where you may want to find hidden fractures before catastrophe happens. So this is the motivation. We want to be able to do wave propagation problems in fracture media. Not every numerical method that you know of is going to be able to incorporate fractures. Let me focus a little bit on the interaction of fractures with wave propagation. To determine the presence of fractures, we need to rely on seismic data in the subsurface. The fractures interact with the wave fields in several ways. For example, there's the presence of anisotropy if we have a parallel fractures, or I mean, they don't have to be exactly parallel. They just need to have a preferential orientation. There's also at the fractures we may see some like high order effects, for example, like phase shifting, frequency filtering. We can see the fracture interface waves and several other interesting phenomena. So the elastic waves are a good way to have an understanding of the fractures. So how can we incorporate fractures in a wave propagation simulation? Well, a traditional approach has been to use what they call the equivalent media. So substitute a fractured media, but by a different media, maybe with anisotropy or viscoelasticity. But there are other ways. I mean, that approach has limitations, and I'm not going to talk much about it because of time. But there are several limitations on that. On the other hand, we can use a numerical method that incorporates fracture discontinuities. Well, one approach has been to incorporate locally an equivalent media. That's one way of doing it. Another approach has been to incorporate like a small heterogeneity with low density and low velocity, which is a rough approximation which yields surprisingly good results. But another approach in which I'm going to focus more here is to incorporate an exactly discontinuity at the fracture location. We call this the linear slip model, and it has several advantages. Overall, of course, if we do a numerical approach, it's going to be computationally expensive. We're going to have to need a lot of computational resources, but we will have very few assumptions. We're not going to be assuming, for example, that the fractures are disconnected, that the fractures need to have certain idealized shapes like penny-shaped cracks, which is a common assumption of EMTs. So there are several methods that have already been proposed to incorporate fractures into the numerical models. For example, the discontinuous Galerkin has been a big champion on this. For example, I show here a few of the papers. We have tested the enriched Galerkin methods in a paper that came out a couple of years ago, and but with some limitations, but we were able to successfully incorporate the fractures. There are other approaches, for example, the generalized multi-scale finite element method and the hybrid Galerkin method, and perhaps a few more. Notice that the classical methods, for example, the classical finite elements, classical finite differences, are not able to incorporate discontinuities. So are basically not suitable to incorporate fractures unless we do like several re-implementation of those methods. But let me focus now on the enriched Galerkin method. So the enriched Galerkin method was proposed in this paper by Sun and Yu. Their application was to simulate transport in porous media. So they considered to enrich the classical Galerkin method with some discontinuous constant functions, element-wise constants. So they do that to make it locally mass conservative. So after the paper that which is fairly recent, several papers have come out that apply this method to different problems, including this paper in 2018 where we use it for wave propagation. But we identified several limitations on this method using constants and even using piecewise linears. So we now propose to use higher order enrichment, to use higher order polynomials as enrichment. This has never been tried before, so we wanted to see if it works for wave propagation. Let me talk a little bit about anisotropic wave propagation, because I realize that some of you may not be seismologists and may not be familiar with you may be familiar with the elastic wave equation, but not the anisotropic version. So in fact, if we include anisotropy, the equation kind of simplifies to this equation that you see here on the left. Notice that, well, rho is the density, but we have this fourth order tensor which incorporates the anisotropy parameters. We call this the fourth order elastic tensor. We can write this fourth order, there are several symmetries, so we can write this fourth order tensor as a 6 by 6 matrix. So let me just mention briefly that for the continuous case, for the classical finite elements, we can write the weak formulation of the elastic wave equation like this, like is shown here. So this is the second order time derivative, and this B term is shown here below. You incorporate the anisotropy with this fourth order elastic tensor. Oh, I have a, this one should be U and B here. I have a typo here, sorry. So this is your classical weak formulation for the usual finite element implementation. So what happens if we want to incorporate, if we want to use, for example, the discontinuous Galerkin method? So since we don't assume that the basis functions are continuous across the element interfaces, we need to add this additional term. This I'm calling here this JC gamma, which is shown here below. Perhaps you're familiar with this. This first term comes out of the when you apply the Gauss theorem to the equation, and then you add these last two kind of arbitrary terms. The first one, the middle one, basically is for symmetry. You notice, compare this to, if you compare this middle term to the first one, you notice that it has kind of a symmetry. And then that's not good enough to impose continuity in case the wave field is continuous. So you need this additional term, which we call it the penalty term, to impose the continuity. So basically, so for enriched Galerkin, we use this same weak formulation that is used for discontinuous Galerkin, but we assume that instead of these discontinuous spaces, we use the continuous basis space and enrich it with some discontinuous space. So that's why we call it the enriched method. Okay, so we would like to be able to incorporate in this weak formulation some fractures, which are not, we cannot include those here, but I'm going to show you how to do that. First of all, let me talk a little bit more about the linear slip model. The linear slip basically says that the displacement field may be discontinuous at the fractures. So these braces indicate that there's a jump discontinuity. So the displacement is linearly related to the traction through this theta matrix, which incorporates the fracture parameters. And so this theta can have several, can be written several ways, but for the usual cases, it comes down to just these two parameters, which I'm going to call theta n and theta t, which are the normal and tangential compliance of the fracture. We can incorporate the linear slip model into the weak formulation, adding this final term JF gamma, which notice that this JF, which is shown here, is basically comes straight from the linear slip model. So now we have this kind of longer, complicated weak formulation, but I mean, it's not really that much complicated than the usual weak formulation. But notice that gamma, I'm defining two sets of element interfaces. One is gamma C and gamma F, which are disjoint. So whenever the wave field should be continuous, we applied this term from discontinuous Galerkin, but whenever we have the fractures, we allow to be discontinuous through this other term. So let me just briefly compare the continuous, discontinuous, and enriched Galerkin method. So the continuous Galerkin in numerical seismology, the most successful method is what we call the spectral element method. It has been quite successful. It uses the Gauss-Lovato-Legendre nodes and quadrature rules, and is very efficient computationally, and is very, very accurate. However, it's not clear how to modify it to incorporate fractures. Basically, I mean, to modify it to incorporate fractures basically brings it somehow to the discontinuous Galerkin method. So the discontinuous Galerkin method has some has advantages, but it also has several disadvantages. For example, it requires a lot of degrees of freedom because the nodes at the interfaces are not are disconnected between the two sides of the element. So there's a proliferation of degrees of freedom. Also, we have noticed that for wave propagation, the stability conditions are quite restrictive. So although it allows to incorporate fractures, it's not exactly what we're looking for. So that's why we wanted to try the enriched Galerkin method, which also allows to incorporate discontinuities, but it doesn't have as many degrees of freedom. We may save a few or a lot degrees of freedom, and we are hoping that the stability conditions are more friendly to us. And I'm going to show you some more of that a little bit later. Okay. So let me show you some results. So this is that's the method I'm going to propose. So we tried first for a very simple. We tried the method first for a simple isotropic model, no fractures, just a simple elastic wave propagation. These are the model parameters. And let me show you first the continuous case. This is actually the spectral element method. And we are using fourth order basis functions. The source is at the center, and we allow it for 0.4 seconds for the waves to propagate. For those of you who are not familiar with this kind of plots, this is just the displacement field, and the fastest wave, the larger circle, corresponds to the P wave, and the inner circle corresponds to the S wave. This is on the left you have the X component, and on the right the C component. And this is the way it's supposed to look. Looks very nice. There's not much error here. For discontinuous Galerkin, we can basically get the same accurate results, but notice the number of nodes that we need here. We have here 90,000, and it's a lot more than what we will require for the spectral elements. And notice that this is a little bit more than 300 time steps, and this is more than double the number of time steps. So you can see here the computational cost of this method. So what about the enriched Galerkin method? So basically using almost the same parameters, basically the same parameters as before, we can get the results with the same number of time steps as spectral elements and not as many degrees of freedom as the discontinuous Galerkin method. However, we can see this bothersome noise basically everywhere. For example, in the right here in the center, this is what we call a grid dispersion error. So this is noisy and this is not good enough. For these results, we have been using, we use the piecewise bilinear functions. So as I mentioned, we wanted to try higher order. So I'm enriching here now with second order basis functions. So you can see that the error has decreased a little bit. However, there's still some noise here, and the number of time steps required to get these results is very good. Is the same as the spectral elements. However, the number of degrees of freedom is comparable to discontinuous Galerkin, so it's already a lot of degrees of freedom. However, we can see that we can reproduce the P and S wave fronts fairly accurately with some marks. We can still go higher. We enrich it now with third order basis functions, and we notice that the number of time steps required goes up a little bit, not that much. However, the number of degrees of freedom has increased significantly, even more than discontinuous Galerkin method. But the results are a lot more accurate, so that's the good part. Okay, let me show you very quickly. I see that I am running out of time, so let me show you briefly an isotropic model. This is the anisotropic matrix, and with some fractures. So I'm using just a random distribution of fractures, and since it is anisotropic, now the circular wave fronts turn out to be somehow elliptical wave fronts, and all this scattering is due to the fracture. This is not noise. This is what we want to see. So this is very accurate results from discontinuous Galerkin. Notice that I'm not using spectral elements because that method cannot incorporate the fractures. And let me compare to the enriched Galerkin method. Using first order enrichment, you can see that there's so much error here that, I mean, the results are not even comparable. So this is not good enough. We enrich with second order, and there's still too much noise to be able to get accurate results. So we need to go a little bit higher. Let me show you with fourth order enrichment. Now, notice that we reproduce all the phenomena related to the fractures. This all looks very similar to the discontinuous Galerkin method. There's some noise that is not present in the discontinuous Galerkin case. However, I mean, the method works quite well, and it's a little bit faster because, or significantly faster because it requires less time steps, although it requires a lot of degrees of freedom. So I guess this is my final slide. So we have formulated this enriched Galerkin method with high order enrichment for wave propagation. I didn't show you results for acoustic wave propagation because of the time, but we have implemented that method as well. So we can see that it's applicable to geophysical models. However, we notice that the polynomial enrichment, the order of the polynomial enrichment is very important to be able to get accurate results. So we need to get as high possible for this enrichment without getting too many degrees of freedom. So the advantage of enriched Galerkin is that it can accommodate fractures. It can require less degrees of freedom than discontinuous Galerkin, and it requires fewer time steps. However, there's some grid dispersion error that we believe is related to the enrichment has lower order than the continuous basis functions. So some further work, we will do some grid dispersion analysis, and we want to compare the results with equivalent media. So I will be happy to answer any questions if there's still time. Thank you.
Thank you very much, Jonas. We've got 8 minutes until the next talk. If there are any questions, please put them in the chat. Here in the phone, I've got the chat under the More button. I click on More, and then I click on Chat. On the desktop version, I think it's a bit more obvious. I have a question from Danielle Castañón.
Can you hear me?
Yes, we can hear you. Okay, Adelante. Go ahead, please.
Hello. Just want to. I have 2 questions. So first, can you clarify if you are using simplices? I mean, triangles in 2D.
Oh, okay, good question. Yeah, sorry. Yeah, I never mentioned that. I'm using quadrilaterals.
Okay, that actually answered my second question. My second question was if it was a version of rectangles or quadrangles of enriched Galerkin methods, but yes, you answered my 2 questions. So, okay, thank you.
So that's a very good question. In seismology, we almost always use quadrilaterals because they yield a lot less numerical error. They have a better grid dispersion properties. So all the results that I'm showing here are for quadrilaterals. Okay. Yeah, good question. Thank you, Daniel.
Okay. No, I answered because I knew that it was usually they use the triangles, but that was for parabolics or elliptic problems. But that was I had this question. But thank you. Nice exposition. Nice presentation.
Thank you.
Yeah, thank you. Any more questions? You're supposed to be able to raise your hand as well if you want. I don't see anybody raising a hand yet. I'm not sure if it's a limitation of my telephone view or if it's a limitation of nobody raising their hand. I'm going back and have a look in the chat. Somebody in the chat asking a question. No more question in the chat for now. Jonas, maybe a stupid question from me. You said that the enriched Galerkin or lowers the order, and that gives rise to spurious noise. If you raise the order of the underlying polynomial, would that potentially offset the effect of the enriched Galerkin, that you then lower the order to a comparable scheme? I don't know if that makes any sense.
No, yeah, that's a very good point, Marcus. Yeah, it's a good question. So basically, I think I deleted a slide because of time. Yeah, I can see where your question is coming from, because I didn't like spend that much time explaining that, I guess. So basically, notice the space that I define here below. So I have this continuous space, which basically yields the classical spectral element method, and then I have additional basis functions which are allowed to be discontinuous. So if I in the first space I use a certain order of bases, and then I use the same order of bases, I end up with the degrees of freedom end up being all of those in the continuous Galerkin plus all of those in this continuous Galerkin. So it will be very costly computational. You might as well just stick to the discontinuous Galerkin method, and you're better off. So that's the kind of, I mean, we need to have a trade-off, not go as high, because then you just might as well use the discontinuous Galerkin method. There will be no advantage. So that's why we want to see how high can we go in the enrichment without ending up with the same or more computational cost than discontinuous Galerkin. Basically, discontinuous Galerkin is very accurate, works quite well, and what we want to avoid is the computational cost of discontinuous Galerkin. So if we end up in that same range, so we lose all the advantages. Am I making sense here? Is that clear?
Oh, thank you. Yes, I was on mute. So thank you very much. That makes sense. Yes. Any more questions? Let me just quickly check on the chat again. No more question on the chat. I would think we use the remaining minutes for the next speaker to get ready, but we'll start on time in case there are any transfers from any other parallel sessions, so they don't miss at the beginning. Thank you, Jonas. Very interesting.
Thank you.